Thank you so much for the introduction. As already mentioned, my name is Svenja Stoehr, and today I want to present to you the results of my master thesis that I carried out at the Technical University of Denmark, where I assessed the effects of mussel reef on coastal marine communities in a degraded ecosystem. So coastal marine habitats such as reefs, seagrass meadows, or kelp forests are of key importance as they provide important ecosystem functions to both marine species as well as humans. So for marine organisms, they increase the habitat complexity and provide feeding sites, shelter, and spawning in nursery areas. And for humans, they create natural barriers to coastal erosion. They can have an impact on the water quality and also enhance the food production. Among coastal habitats, shellfish reefs are considered as hosts of some of the most diverse communities and create biodiversity hotspots within the coast areas. And the most dominant mussel species in Danish marine waters is Mytilus edulis, and the most common benthic filter feed in the Baltic Sea, forming reefs. However, these reefs and other coastal habitats are facing many anthropogenic pressures, including climate change, overfishing, and eutrophication. And around the turn of the century, it was estimated that 85% of the European coastlines are degraded, which meant a loss of important habitats, including biogenic reefs such as mussel reefs. The EU implemented several marine strategies, including the EU Habitat Directive, as well as the Water Framework Directive, which had the aim to overall protect vulnerable species and habitats, including blue mussels, and to also reduce eutrophication and achieve an overall good ecological status in all European surface water bodies. Now here we can see a map of my study site, Helnes Bay, which is located in the south of Denmark. And this site has historic records of large coverage of mussel reefs. And despite a ban that was introduced to prohibit the use of bottom contacting gear, mussel dredging was still allowed, which led to a drastic decline of the reefs within the bay. In 2010, there was a mussel reef restoration project by the university, together with local stakeholders, which established 45 tons of blue mussels within the bay, which led to a small recovery of the mussel beds. However, in 2018, a commercial dredging company then surveyed the area with the interest of mussel dredging within Helnes Bay. This was met with strong resistance, which achieved a reinforcement of the ban in 2019, and this time mussel dredging was included. Now, supporters for the dredging argued that the bay is likely already in a poor ecological status anyway, and therefore the protection of these mussel reefs would be less important. And this is where my project ties in. So I aim to demonstrate the importance of these mussel reefs even in a degraded ecosystem. So I had two objectives. First of all, the assessment of the environmental status in Helnes Bay. And then secondly, I wanted to investigate the effect of mussel reefs on mobile coastal fauna by comparing the reef sites to bare sandy bottom control sites. I had three hypotheses. First, Bay will not fulfill the requirement of a good ecological status as it is set by the Water Framework Directive, but that nonetheless the mussel reefs would enable higher biodiversity, and that lastly, the species community composition will be significantly different between the two compared habitats. The first step was the environmental status assessment, which was carried out according to the Water Framework Directive classification system, which applies indicators in order to classify the status. Different European countries use different indicators. However, one of the most commonly used ones is chlorophyll A concentrations, which functions as a proxy for phytoplankton biomass, which is enhanced by eutrophication. There's a monitoring stations located within the bay, which has been recording data since 1983. So I had almost 40 years of chlorophyll data. Additionally, in Denmark, they also use eelgrass depth limit as an indicator, which is defined as the maximum water depth to which eelgrass can grow, which is a valuable indicator because it responds to visibility and light availability, which in return is influenced by eutrophication. Eelgrass surveys were carried out in the area between 2000. For the statistical analysis, I calculated one annual mean value for each indicator and also formed a 6-year average value. And these were then compared to reference values, which reflect the conditions without human impact, and are usually obtained from either modeling or historical records. The second step was the community analysis. This was based on data that was collected in the spring of 2019 using beta remote underwater video systems, also called BRUVS. And here we can see such a setup. So we have a metal frame to which cameras in watertight housings are attached to. And these frames are set on the seafloor to record. And in front of the cameras, there is a bait arm with bait attached to it. And this bait creates an order plume around the camera and attracts fish towards it so they can be observed. These camera frames were set on the seafloor for 1 hour. Here we can see the study site Halnes Bay. The yellow symbols indicate the mussel reefs, while the blue symbols indicate the control sites with sandy bottoms. It was also deployed at 2 different depths. So we had intertidal sites that ranged between 0.5 and 1.5 meters and are represented by the circles, as well as deep subtidal sites, which were ranged between 7 and 9 meters and are the triangles. On the maps, we can also see the locations of the eelgrass surveys. Those are the green squares, and also the monitoring station, the red dot, which recorded the chlorophyll. Overall, 115 deployments were successful, and then further to video analysis. Here, the observed organisms are identified ideally down to species level, otherwise to lowest taxonomic level. And then they're quantified using relative abundance instead of total abundance, which means that not all organisms that are recorded in the video are counted, but a relative abundance measure called max N is used, which is the maximum number of organisms within one frame. That helps to avoid bias from organisms leaving and re-entering the camera frame. For statistical analysis, firstly, I calculated diversity indices for each of the deployments. So I calculated species richness, Shannon-Wiener diversity, and Pelous evenness. And then I applied generalized linear mix models to explore the effects of depth and mussel coverage on the 3 chosen diversity indices. Then I also carried out multivariate analysis using NMDS and CUP, as well as an indicator species analysis to assess the community composition, as well as the association of species with specific habitats. Results. The environmental status classification was carried out using the face value approach, which means that the status is classified solely based on the mean value and disregarding the confidence intervals. For the eelgrass depth, here we can see there's no clear trend over time, but overall the ecosystem is constantly in a moderate status, which is also confirmed by the 6-year average value. Then for the chlorophyll A concentration, here we can see there's some stronger fluctuations over time, with the indicators fluctuating between moderate and poor. However, if we look at the more recent years, we can see that it mainly ranges in the poor status class, which is also confirmed by the 6-year average value. Overall, the Water Framework Directive calls for the application of a one-out, all-out principle, which means if one of the indicators fails to meet a status class, the entire ecosystem fails this status class. So we can say the ecosystem is in an overall poor status, which reflects the situation in the majority of Danish coastal waters, as only 2 out of 119 evaluated water bodies in 2021 reached a good ecological status. And with good ecological status, we see the green status class that is supposed to be achieved. Now, despite this poor ecological status, effect of the mussel reefs, so overall, we observed 25 species across 115 deployments, and the number of unique observed species was significantly higher at mussel reefs compared to sand sites, both at shallow as well as deep sites. So there was an overall positive effect of mussel coverage. When looking at the Shannon-Wiener diversity, for shallow diversity was higher than the sand sites. At deep sites, there's still a slight trend visible. However, this was not significant. In the end, we still had an overall positive effect of mussel coverage on the diversity. And lastly, when we look at Pelous evenness, there was no significant effect of the mussel coverage or depth on the evenness. However, we observed a negative effect of visibility, which means that the higher the visibility, the lower likely be related to the methodology, as it heavily relies on visibility. So overall, the mussel beds likely provided better structure that improved the fish habitat on a local scale. So the higher complexity led to a more abundant and diverse species community, and the removal of the mussel reefs could have severe effects and local species extirpation. So now we wanted to look at the community composition. Here we have an unconstrained ordination with the NMDS. All sites were grouped by, or all deployments were grouped by site ID, and we can see a clear separation of both sites based on mussel coverage, but also depth. This was also confirmed when we constrained the ordination. So here we have a canonical analysis of principal coordinates, where the Ordination was constrained with the environmental variables, so the x-axis represents the mussel coverage and the y-axis represents the depth. And again, we can see a clear separation of all sites. We can also see that certain species were significantly responsible for these differences. To further investigate these species, we carried out the indicator species analysis, which revealed relationships between species and specific habitats. Overall, 10 species were associated with one or multiple habitats. However, in the following, I will only evaluate the ones that were associated with the mussel reefs. The first group were the common starfish, which was associated with subtidal deep mussel reefs, and the European flounder, which was associated with deep sites in general. And both of them are predators for mussels, which means they heavily rely on them as a food source. Removal of mussels by dredging could have severe effects on these species. Now, one might argue that this predation effect on the mussels could also have severe effect, but even the empty mussel shells still provide many ecosystem services and support diverse communities besides the absence of live mussels. So the mussel reefs are still highly important for the species. The next group were a group of small mesopredators, including 2 stickleback species, which were associated with the intertidal mussel reefs, as well as 2 goby species, which were associated with high mussel coverage in general. And these mesopredators may prey on smaller invertebrates that are found in high abundances within the mussel beds. So they heavily rely on them for food provision. Also utilize the mussel reefs as shelter from larger predators, as well as spawning sites, as black gobies and other goby species are known to attach their eggs to the mussel reefs. So all of these species rely on the mussel reefs throughout many different life stages. It's found to be associated with low mussel coverage sites, which is also reflected in literature where they usually prefer soft bottom habitats. However, they are often still found in proximity to mussel reefs as they also rely on them as a food source. The last significant species with shallow mussel reefs was the garfish, which is a predator that feeds on smaller fish such as the mesopredators that I just presented. So it also heavily relies on the mussel reefs for hosting these species. Overall, the mussel reefs, as I showed, provide many important ecosystem functions and support many different species. So a removal of the mussel reefs could lead to decline in species abundance and local species extirpation. There's also an important role for commercially important species. So while we did not observe any direct association between commercially important species and the mussel reefs, they might still indirectly rely on them. So both cod and flounder, which were observed in the deployments or in my data, account for the majority of Baltic Sea fishery landings, and the mussel reefs provide them with food. So for the flounder, as we saw, they provide them with food directly as they prey on the mussels, but also for cod, they rely indirectly on the mussel reefs as they host their prey, which are smaller fish. There are, of course, certain limitations to my study. Some of them were related to the methodology. Baited remote underwater video systems use bait, and the presence of the bait might favor the attraction of certain fish species over others. Thank you. Over many organisms that were actually feeding on the bait. And the limitations is that the method heavily relies on visibility, and also the observation of larger fauna and mobile fauna is favored over smaller immobile fauna. And lastly, the relative abundance gives some limitations when you want to compare it to other studies, as often other studies use total abundance. There was also a lack of temporal coverage. As I mentioned, the data was only collected within 1 year and 1 season. So we are not able to investigate how the mussel reefs might be used during different seasons. Also, the data was only collected during the daylight hours and not at night. So mussel reefs might be used differently at nighttime. And lastly, there are some improvements that could be done for future studies. It could also be interesting to invest mussel reefs in less degraded ecosystems. However, this might be difficult, as I just mentioned, large areas of the Danish coastline are severely degraded. So as a conclusion, I was able to confirm my hypotheses that the ecological status was poor, but nonetheless the reefs hosted higher species richness and higher diversity, only the evenness was the same between sites. Mussel reefs are used for a multitude of services, including shelter, feeding, and reproduction, and the removal of these mussel reefs could have severe impacts. Therefore, they continue for their protection. Also, as the removal of the mussels could lead to a further decline in environmental status, as they have a mitigation effect by filtering the water. And lastly, it could also lead to extirpation of the species that are associated with the reefs and overall shift in trophic networks. Lastly, I think this project also clearly demonstrated the value of local stakeholder involvement, as local fishermen were not only involved actively in the restoration efforts, but they were also the first one to step into action when the initial plans emerged to dredge the bay again. And they were an active driving force in the reestablishment of the ban. So I hope that my results also be a helpful resource for the continued protection of both Helness Bay. With that, I want to say thank you for your attention, and also thank you to everybody who supported me throughout the duration of my master thesis. And I'm looking forward